Okay, so let's consider parallel transport now in a more general setting than we have in the past. Okay, we've already seen that parallel transport of a vector around a geodesic triangle did not yield the same result at the beginning at the end of the excursion. Okay, we had lots of examples of that, and we showed pictures and balloons showing the dependence of parallel transport on the path that's taken. So parallel transport is path dependent. Okay. Okay. So I take a vector and I parallel transport it around a closed curve on a general surface, and in general I'm going to get a non-zero result because of the curvature of the surface itself. I want to make that sort of thing quantitative, and I want to write it in a way that I can apply it to many situations. Okay, you know what that means in this course? We've got to look for a differential statement of parallel transport, and we're interested in differential equations, okay, to capture the general case, and then applying them to specific cases globally will involve integrating up those differential equations. But the fundamentals, the local theory, okay, is in simple differentials. So for example, I might consider an infinitesimal path and consider parallel transport around it. So I might put down a mesh on my surface, a UV mesh of some variety, as usual, and I'll start at a point P and end at a point Q. Okay, and instead of starting at P and coming around back to P, let me go from P to a point Q. Okay, the statement would be that parallel transporting a vector in different paths from P to Q should give me different results, and that's what I want to find. So here's one differential path. I go first in the U direction and then in the V direction. That's path 1. I get to the point Q, and I've parallel transported my vector. And then I might go in another way. Well, let's do V first and then U, and get back to Q. Okay, and the result is generally going to be different. Okay, so I'm going to express that difference, and I see that difference can be nicely framed by calculating the commutator, okay, of the components of the covariant derivative in the U and the V direction. So here I have covariant differentiation in the V direction and then the U direction, and I want to compare it to covariant differentiation in the other order. In other words, go on one path and then on the other path. Okay, that's a commutator. Claim is that commutator is non-zero. Okay, that commutator is non-zero. It's going to be a measure of the local curvature at the point where I evaluate it. Okay, that's holonomy, and that's what we want to pursue today. Okay. Okay, and so I'm going to express things in terms of covariant differentiation, so that I can along a mesh, so that I can apply it in a general case, and again, to build up a general case, a general vector field that lives on the tangent space, I want to first understand the holonomy of my coordinate mesh itself. So what's the commutator applied to R sub U? Okay, one of the vectors along the mesh in the U direction. And similarly, what's the commutator of the covariant components of the covariant derivative in the other direction, R sub V? Those are the things we want to figure out. Okay, and we've done the preliminaries to do this. Okay, here we go. My goodness. So this is one of those cases again, where there's some algebra. So get out. Okay, get out. Supplementary lecture number 9. Okay, and there you can follow along and see the algebra and verify it. There's even some work you'll have to do following along with an electronic version of this or paper version of this lecture. But I know it's a hopeless mess to look at this poster and do the details. Okay, but so let's just emphasize the concepts, and I'll tell you how the algebra goes. And it's we've done so many preliminaries, and now it's just a question of remembering things. Memory is more significant here than actually doing a complicated calculation. Okay, so what I want to do, I have to calculate I have to calculate the commutator applied to the rate of change of r in as a function of u. Okay, but now I can go back and I can remember how I parameterized those components in the past. Remember when we discussed the excellent theorem of Gauss, we began by differentiating the triad r sub u, comma r sub v, normal. Okay, and so we looked at the derivatives of those vectors and used that as the basis for a derivation of Gaussian curvature. So I'm going to pull one of those equations out. Here's r sub uu. How did we write it? Okay, well, it's a vector in 3 space, so there's components in the tangent space. We introduced the Christoffel symbols to parameterize the components in the r sub u direction and the r sub v direction, like this. And then there was the component in the normal direction, and its coefficient was e of the second fundamental form. Okay. Okay, but now let's just change the language. Okay, here's the second derivative. It has a component in the tangent plane and a component outside the tangent plane. So I see that this means that the covariant derivative of r sub u in the u direction is just the bits in the tangent plane. Okay, so that's easy. Nothing new to be done. Okay, we have these Christoffel symbols, okay, with their funny indices. The funny indices, of course, will be interpreted concretely when we turn to Riemannian geometry. For the moment, they're just labeling the different Christoffel symbols. And remember, the Christoffel symbols depend upon the coordination you use. It's pretty obvious. Okay, and it can be written down in terms of the metric and the gradients of the metric. Okay, E, F, and G in the mesh UV. Okay, and we've seen those expressions, and we've used them, and we're going to see them again. Okay, they were important in calculating curvature. Okay, so there you go. So here's the application of the covariant derivative d by du to this fellow. Then I want to apply d by dv to it, and then I'm going to do it in the opposite order and form the commutator. Okay, well this is easy now. I'm just going to apply d by dv to this fellow. Okay, so here it is, and I differentiate it. Okay, in the u direction. Okay, and I only keep those components, which reside in the tangent plane. That's the definition of the covariant derivative. So I get a slew of a slew of things, right? Because I have this expression occurring twice, okay, from my two covariant derivatives, and then in addition, here when I have the covariant derivative with respect to nu, I'm going to have to differentiate the Christoffel symbols with respect to nu as well. So in addition to getting products of Christoffel symbols from having two covariant derivatives, I'm also going to have terms where I differentiate the Christoffel symbols as well. And so I've written that down here. Okay. So that's straightforward, but check it on the side. You see the kind of terms I expect to get, and I get them here. Quadratic terms when I apply this expression twice, and then when I differentiate this expression, okay, I'm going to find the derivative of the Christoffel symbol itself. Okay, so there you go. So there's some arithmetic to be done. Okay, in every place where I see multiple derivatives of r with respect to u or v, I have to apply this formula, and I get the quadratic expressions of the Christoffel symbols. I have to look back at my discussion of the theorem of Grecium and get the other components. I've just shown you r u u. You're going to have to look at r u v and r v v as well to get everything together. That's why you have the Christoffel symbols here with the different indices, because you had to look at r u v and write r u v in terms of the tangent space. So straightforward stuff to do. Okay, it's just algebra. Okay, and it's a tad messy. no doubt about it. But there you go, and check me, and it's in the lecture notes. We had a similar expression when we do the covariant derivatives in the opposite order, okay? And then I take the commutator, I take the difference. Okay, and that's what I've accumulated here. So I've done all that arithmetic. It takes me a page of algebra and considerable care to get my indices right. Okay, and so then I'll get this commutator acting on RU. It's a linear superposition of the basis vectors in the tangent space RU and RV. Okay, I have to do the arithmetic to get rid of the second order derivatives, writing them down to first order derivatives using expressions like this, and this is what results. So I have derivatives of Christoffel symbols, then quadratics of Christoffel symbols in that collection in the U direction and the V direction. So you look at that and you say, oh my God, I'm lost. What a mess. But then you go back to the algebra that we did for the Gauss's excellent theorem, and you see, in fact, these creatures, you've seen them already. They're just hiding the curvature times F. And this bracket is hiding the curvature times E. Ha! It's the curvature that's hiding here, okay? This isn't just a gobbledygook. It's just a explicit expression of the Gaussian curvature. So go back, okay, to the derivation of the excellent theorem, and you'll see that this combination we already identified as minus Fk, and this combination was Ek. So it's important to remember that stuff. Okay, so now we've made a little bit of progress, but there's more to be made, because now we can easily combine these two terms like this, common factor of k, and then I have this expression here. But you see now I want to pull out the geometry, because I know that E is just a dot product of RU with RU, F is a dot product of RU with RV, and I've written that out here. So then I get K, just the scalar, okay, just the curvature, times this collection of stuff. And if you look at that for a minute and remember a little bit of vector calculus, you see that that's a triple cross product. Okay, you've just written out a triple cross product. So it's K times RU cross RV, quantity crossed into RU. Okay, and then we show it over here. Okay, here could be RU. Okay, like that. Okay, and here might be, and you have an RV in some direction over here, and the normal is the cross product as indicated over here. So RU cross RV, that points in the n direction, then I have to take n cross RU, and what do I get? Okay, well I get a vector, okay, that's perpendicular, that rotates RU by 90 degrees, right? N is in this direction, cross it into RU, that's what I'm supposed to do over here, because that's what all this stuff boils down to, and that's just the rotation of RU through 90 degrees in the counterclockwise direction. Okay, so now I can identify things. Okay, I got RU cross RV. Okay, that magnitude, so I've indicated magnitude, and the direction of the triple cross product is 90 degree rotated RU. Okay, so here's the magnitude. Okay, the magnitude of RU cross RV gives me this. Okay, the rotated vector carries a magnitude of RU. Okay, but it indicates the direction of the result. Okay, so I can either write it this way or this way. Well, sometimes I like writing it this way, because here's K times, this fellow again. Well, he's familiar. He controls the surface area. He's the element of surface area, and this is a direction. Okay, so either way you like to write it. Okay, we'll flip from one discussion to another, because it's K times the surface area, which comes into the Gauss-Bonnet theorem. So it's a good thing to pull that out and have the direction separate. So there you go. So I've got one of the commutators. Now I'll do the other commutator for a applying to R sub V, and lo and behold, and you know, as you can imagine, it's again of the same structure. It's non-zero because the Gaussian curvature may be non-zero, and then I have the vector character of the commutator applied to a vector in the tangent plane, and that's what controls it. So I've written it down like that. Okay. Okay. So that gives you then the holonomy expressions for the vectors in the mesh, defining the mesh. And if you want a general case, well, for example, you want to apply it to a vector field V on a surface, just take V, okay, and use R sub U and R sub V as the basis in which to expand it. Okay, so V applied to the mesh at a point P on the surface is then some coefficient times RU plus another coefficient times RV, and then you see by linear, knowing our result for RUs and RVs, I can get the general result for a general vector field. And I'm not going to do the arithmetic here. It takes a little bit of care, but it's no great surprise, okay, that the structure of the holonomy now applies to this case of a general vector V. The commutator applied to the vector V is non-zero because the Gaussian curvature is there. Then I get cross product of RU cross RV crossed into V. So it's just a linear superposition of the expressions that I've already had, and you have to be a little bit careful when you do your derivation because A's and B's have U and V dependence as well. So take a look at that. It's nothing special for differential geometry. Just be careful with your derivatives. Okay. So now we have this expression, and lots of our early examples of parallel transport can be rederived now from this. And this shows us very clearly, okay, at a very fundamental level, that it's the Gaussian curvature, okay, that's responsible for the fact that parallel transported vectors along closed paths can be expected to be non-zero. Okay. Okay, so let's go back to another one of the applications of interest, which was geodesic deviation. Okay, geodesic deviation being very important in applications of general relativity to experiment and to theory as well. Okay, so I'll take my Gaussian polar coordinates and then just apply it to the holonomy expressions that we've already had. Okay, because once I have polar coordinates, you know, then I can discuss how quickly geodesics deviate from one another as rho increases, as the distance from an origin increases, and that's what's of interest in the case of geodesic deviation. Okay, in the applications to general relativity, for example, we're interested in, for example, tidal forces. Okay, 2 points which experience gravity. In other words, they're in free fall in a gravitational field. Okay, space-time is warped by the presence of perhaps a nearby black hole, and so the distance between those two points, which are traveling on geodesics, okay, because they travel on geodesics because they experience no forces, okay, they are just moving in a gravitational field, okay? But they may come together or move apart depending on the local Riemannian geometry. Okay, in the case of four-dimensional Riemannian geometry, we have a tensor to express curvature, and so we'll have geodesic deviation equations of a tensorial character like that. Well, why is that important? Well, that's how gravitational waves were detected, right? You had two freely hanging mirrors, very far apart, a couple kilometers apart. A gravitational wave, came between them. Ever so little changed the distance between them, the geodesic deviation. Okay, how much is a metric affected when the gravitational wave pushes through that area? very small effect, but you measure it by looking at how freely falling objects, okay, how the distance between them is affected as it moves through. It's a tidal force kind of thing. And so the equation for the geodesic deviation in the context of Riemannian geometry allows you to measure the presence of a moving gravitational wave in your environment, because a gravitational wave is a wave in the metric. Okay. And so this is the basis for all of that snappy stuff. Okay, so let's just do our preliminaries here. Okay, so I'm going to write my Holonomic expression in the case of Gaussian polar coordinates. So U becomes rho, the polar geodesic, and V becomes theta, the angular variable perpendicular to rho. And then I'm going to write it out for the case of the tangent vector along the geodesic, the radial geodesic. And so I've just done that. This is nothing new. This is just an application of the equation, this equation that we've already derived. Okay, but it simplifies, because for theta fixed, R of rho and theta is the radial geodesic, and so the tangent to the radial parallel transports. So one of these terms disappears completely. And then on the other term, you see I have R sub rho hit by the covariant differentiation in the theta direction. Okay, and so I write that down here. And here I have the second derivative in the theta direction and the rho direction. This is a covariant derivative, so only the bits in the tangent plane contribute. So I write it as an ordinary derivative, and then t meaning projected to the tangent plane. And then I've accounted for the fact that it's a covariant derivative in the theta direction that applies there. I'm going to clean up this term a little bit, and so that's why I'm doing this manipulation. Once I have it as a second derivative in the tangent plane, I can reverse the order of those differentiations in the tangent plane, because that's just ordinary differentiation, and those components commute. And once I write it like that, then you see I can write it then as dr by d theta, and then the covariant differentiation in the rho direction. So I'm able to switch the rho and the theta in this expression as shown here, and end up with the covariant derivative of r sub rho in the theta direction is the same as the covariant derivative of r sub theta in the rho direction. So I can switch those indices around, and that cleans everything up. Because now I come back to the left-hand side of this expression. Okay, I write it down. I apply it to the case of a geodesic, and so one of the terms, this term completely disappears, and then this term here, okay, I can clean up using my expression here. So I can trade the d theta r sub rho, for d rho r sub theta, okay, like this. Okay, so then I get a second derivative of r d theta, okay, dr d theta, the vector in the theta direction, okay, over here, and then I get the other term in my equation, and I can pull that over on the left-hand side. Okay, watch the minus sign here, and then get that expression is equal to 0. Okay. Well, we've seen expressions like this before. When we were studying geodesic deviation on the sphere, we wrote down this expression for the geodesic deviation between great circles. It was second derivative of epsilon with respect to arc length was minus k times epsilon. We conjectured that might be more general, and here's the generalization of it. See, second derivative with respect to arc length, that's what I have over here. Except, okay, in the general case, it's covariant derivatives. Okay, that's fine. R sub theta being like epsilon, the distance between the geodesics, and then the result being that that k makes the second derivative non-zero, and then I get some geometry to show how the direction of the deviation. Now we have this is now our general result, and that's called a Jacobi equation. Okay, and I'm writing that out, and I'm writing that out here. Okay, so I'm going to call R sub theta J of S a Jacobi field. I'll write rho as S. It's the geodesic distance, and we have a simple example of what's called the Jacobi equation. So I'm being particular in my order of my operators here to get things quite right. Okay, and J of S is then indicative of the distance between the geodesics as I move out of the point P in a geodesic distance S. Okay. Now, when we discussed the sphere, we took a special situation, and let's re-express that analysis in this language. Okay, this language you see is exact language. Okay, and we can re-express what we did on geodesic deviations on the sphere. So let's do that. Let's imagine that we're moving along the equator through an angle pi. Okay, and I have one vector which is r in the phi direction. Okay, so that tells me the direction of this equator, of this great circle. Okay, and then I have a distance perpendicular to it. Right, that's what I'm interested in here. What's the perpendicular distance is doing as a function of the arc length around a geodesic. So I'll apply that here. So I suppose U of phi is parallel transported along the equator, so it satisfies this condition. Okay, and I see also from my picture that R sub phi dotted into U is 0 along the equator. Okay, simple geometry. This is the geometry that we studied before, and I claim that J, the parallel transported vector times sine of phi, is a Jacobi field. That is, it's going to satisfy this equation, and it gives me a sense of how rapidly the great circles deviate from one another for this particular geometry. Let's prove it. Okay, so I want to take the second derivative of the Jacobi field with respect to S. Okay, so in this particular direction, my arc length is parameterized by phi, so I differentiate it with a covariant derivative. The covariant derivative hits U, but U, you see, is parallel transported by definition, so that gives me 0. And I just hit the sine function, okay, which differentiate with respect to phi gives me cosine. And then I do it again. That's what I'm supposed to do it again. Same analysis. The only thing that changes is cosine becomes minus sine by differentiation. So I collect it all up. Okay. So here's my second derivative on J. It's just minus sine phi times U of phi, and my other term here, okay, is just k. In my case, for a unit sphere, k is equal to 1. Okay, and then I have to do these. These cross products. These cross products here. In the case that J is equal to U times phi of theta. So the phi of theta comes through, and then the vectors themselves. Well, I have an R sub phi crossed into J. R sub phi crossed into J. That's out of the picture, and then I have to cross that into R sub phi out of the picture, cross it into R sub phi. That's in the U direction. Okay, so it reproduces the U direction, the cross products there, and so I have minus sign plus sign. I get 0. Okay, so there I made for you a Jacobi field, and we see it has the character of our example for the sphere. That is, the Jacobi field, it vanishes when phi is 0. It vanishes when phi is pi. Okay, the geodesics that started out at 0 come back to themselves at pi, and then they satisfy a harmonic dependence upon the arc length that you travel. Okay, so the maximum distance is halfway between 0 and pi. Okay, where sine is 1, and that's the result that we had before. Okay, so the geodesics at phi equals 0 spread sinusoidally along the equator, and they merge again at phi is equal to pi. Okay, so that's what we wanted to do today, and And now we're ready for a little bit of a change. We're going to start doing some special topics, lectures, and starting next time. We'll go back to one of our favorites, the Gauss-Bonnet theorem, and we'll discuss it for piecewise closed curves, and then we'll discuss it for entire surfaces with handles, and we'll discuss triangulated surfaces a bit. A little introduction to global topology of surfaces. Okay, I'll see you then.